look at, on Torn, there are two ways to look at this. One is to look at the textbook on page 308. So on page 308, we have these rules that sums satisfy, that adding up a bunch of terms that look like a list A sub k and a list B sub k, you can add up all the first ones first and all the second ones second. That's just the idea that addition of numbers can be reordered. Same thing for subtraction, right? If I take the AK minus BK, so I've got two different lists of numbers. If I take the number in the first list minus the number in the second list and add up those differences, that's the same as adding up the first list entirely and subtracting the second list. If you're a cashier and you've ever had to cash out a register, or reconcile a register tape, you've done this. You know how much you started with at the beginning of the day, and you can add up all the money that came in and subtract off all the money you gave out, and what you should have is how much money is left. Or you can do that transaction by transaction. This says the distributive law of addition for it. So you can take, if everything is a multiple of 5 and you're adding them all up, you can factor out the 5. And this says if you take a constant and add it to itself n times, you get n times the constant. So we'll use these rules, and they'll hopefully will become kind of automatic. But if you take this first one, says something about, just to clarify that a little bit, what this first one is talking about is if you take 1 plus 4 plus 9, the general term is k squared. If you add the sum of the first n perfect squares, that's what that's giving you. So the shorthand for that is starting with k equals 1 and incrementing by 1 until you get up to k equals n. You're taking the value of k, squaring it, and adding it to the accumulated sum. Now let's take a look at what this says. The thing that's changing in each term here is k. The total number of terms, n, doesn't change. If you look back at when I wrote out the first couple of terms over here, which was here, the only thing that's changing is this number k. So if I look at this sum, I can view this, well, this 1 over n is a constant. It can be factored out because we have a rule that says that constants factor out. And so this can be thought of as the sum, k going from 1 up to n, of 1 over n times, this is 1 minus k squared over n squared, which is 1 over n times the sum. I can rewrite that as n squared minus k squared all over n squared, just getting a common denominator, which I can think of as 1 over n, k going from 1 up to n. That thing in the brackets can be written as 1 over n squared times n squared minus k squared. That's 1 over n times 1 over n squared, because you see at this point, n doesn't change from term to term. It's a common factor. It's just 1 over the square of the total number of terms. And what I'm left with is the sum, k going from 1 up to n, of n squared minus k squared. So this is 1 over n cubed on the outside, and then I have the sum from 1 to n of n squared minus the sum from 1 to n of k squared. That's 1 over n cubed. What happens if I add n squared to itself n times? And so this first one is just n times n squared. And then we had a formula that said the sum of the first n perfect squares is n times n plus 1 times 2n plus 1 all over 6. The important important feature here is that we've taken this general expression that's a long sum. And keep in mind, we want to let n get really, really big. And we've rewritten it as something that depends only on n. And so if we look at trying to further simplify this, we have a 1 over n to the third. This is n cubed minus 2n cubed plus 3n squared plus n all over 6. Which is 1 over n cubed times 6n cubed minus 2n cubed minus 3n squared minus n all over 6, just giving a common denominator, which can be thought of as 1/6. 6n cubed minus 2n cubed is 4n cubed minus 3n squared minus n all over n to the third. So they asked us to compute a Riemann sum. We did. We've gone through and written out that Riemann sum so that it's now a function of n, which it should be, right? It depends on how many pieces you chop the interval into. Once you change the number of pieces, you get a different thing, but it depends on n. Now, what happens to that is if we let n go to infinity. This thing goes to, this n goes to infinity. Well, there's a 1/6 there. And now, what about the thing in the brackets? What's the limit of that as n goes to infinity? 4. And the answer is going to be 4. Ought to be 2/3. Remember what the question was. We got to remember what the question was. You got this function y equals 1 minus x squared, and you're trying to approximate the area, or you're trying to get the area under the curve. The difference is that we saw that if n gets bigger, we get better and better approximations. But if we take the limit of those approximations as n goes to infinity, this is no longer an approximation. This is the exact value of the area under that curvy thing. And that's what integral calculus starts out looking at, is how do you find exact areas under curves.